Hello and welcome everyone. It's absolutely wonderful to have you here. So we do appreciate you joining us for this very special event. We are also absolutely delighted to be joined by our partner Geffersoft as we introduce a new interlayer for head-up display technology. With this next generation head-up display interlayer, more information can be brought to the driver's attention. Extending the virtual image distance from today's current range will enable larger field of views and augmented reality without compromising on optical performance. Just imagine how this improves a driver's reaction time. That's why optical performance is so important. New head-up displays will enhance driver safety by augmenting the driver experience with clear, pertinent, real-time information out in front exactly when and where it's needed. For this portion of the presentation, let's welcome Jonathan Gutman. He works in sales and project management for Geffersoft's HUD inspection projects. Geffersoft develops, manufactures and sells automation systems for complex tasks in multiple industrial sectors, including automotive. The company provides state-of-the-art image processing and laser processing systems that meet each industry's highest quality requirements. Hi Jonathan, welcome on stage. Thank you so much for joining us today from Geffersoft. We're all very excited to hear your presentation. Thank you.
Thank you very much. Hello together, and thank you very much for inviting us to this great event. It's a pleasure to be here, having a talk about such an interesting topic today. My name is Jonathan Gutmann, and I'm the responsible project and sales manager at Geffersoft company for various head-up display projects. Today, my topic is head-up display windshield inspection for long virtual image distances, called LVIDs. So let's go straight into the topic for today. First of all, I'd like to give you a brief overview about our company, Geffersoft, who is a main player in the area of head-up display. After that, I'd like to explain you how the head-up display windshield test benches are working in general. And last but not least, I will come to the challenges as well as the solutions that we have faced concerning LVID and AR HUD. So here on the picture you can see an image from our headquarters in Regensburg, which is a beautiful city in Germany. And Geffersoft is a special equipment, design and engineering company which is owned and managed by our founders that you can see on the screen. The company was founded in 1995 and we have more than 160 employees in the meanwhile. With an annual revenue of approximately 20 million euros, we have an export rate of around 50%. We have gained a lot of HUD experience in the last 19 years, and we are a global leader in automated optical HUD inspection. We have 26 test benches in 9 countries on 3 continents, and we are inspecting more than 90 different windshield models of 15 OEMs. So coming to the HUD test bench, every single windshield which will be built into the car needs to be measured and inspected concerning their HUD functionality. And that's what we are doing with our test benches. Here you can see one of our test benches, and probably you noticed that the windshield is positioned at the very exact position at the test bench as it is also positioned in the car. And that's the concept that we are going for. We have mainly 3 components when we are talking about windshield test benches. First of all, we have the camera. The camera system is mounted on a 5-axis system and is representing the driver and furthermore the eyebox positions. Then we have the windshield, which can be placed by a worker or by a robot onto the test bench. The position of the windshield is defined by the movable slide as well as by the windshield frame itself and the support and reference points. And finally, we have the light source. Here we have mainly 2 options. Either we can use a projector which we all know how it is built into the car, or we can even have an improved projector using a steel mirror inside, or the alternative is to use a test grid which is imitating a HUD projector. Of course, the test bench needs to be calibrated, and this is to ensure the stability and the correctness of the measurement. For small virtual image distances of up to 3 meters, the calibration target is mounted at the position of the virtual image. The calibration generates the transformation ratio from pixel values to the real-world millimeter coordinates. And to sum it up, this is a very compact solution for a standard HUD image distance. As we have seen in the beginning of this event, head-up display continued to evolve and new solutions are being developed and to further enhance the driver experience. We see that the virtual image is getting bigger and bigger, and AR HUD becomes more relevant. And this, obviously, this development implies new challenges. And in this presentation, I would like to address 3 main challenges that we have faced. First of all, there's the camera calibration aspect. As we have longer virtual image distances, we also see bigger pictures of virtual images, which needs to be tested, obviously. And on top of that, when we are speaking about AR HUD, the preciseness and the positioning is getting more important. Other than that, we have the challenge to generate a good test pattern. We always try to provide a durable and stable system in order to inspect windshields. And therefore, in most cases, it's not desired to use a HUD projector. We rather go for a test grid because it is more stable. However, due to the fact that the virtual image is getting bigger and is growing, the positioning of the test grid is getting more difficult. Here we need to find new solutions. And finally, we see a variety of optical phenomena. For longer virtual image distances, we see greater and bigger influence and impact on astigmatism effects. We also see focus shift within virtual image of up to 4 meters, and the aim is to reduce unwanted optical phenomena. So let's come to the probably most interesting chapter for today. As I mentioned, 3 main challenges that we had. I will also talk about the solutions that we have found. And here on the screen, by the way, you can see one test bench which is especially equipped in order to be able to test long virtual image distance head-up displays. And I highlighted the special features that are necessary for this. And I will talk about them later as well. So the first topic is the camera calibration aspect. The aim of the calibration itself is to determine the position of the camera in relation to the calibration target. Then, with this position, it's possible to place the set points at the very correct position of the virtual image. And therefore, we developed a calibration procedure with a movable calibration target. We have 4 steps for this calibration. The first one is the intrinsic calibration, and the aim of the intrinsic calibration is to get the distortion parameters as well as the detailed focal length. The second step is the extrinsic calibration of all eyebox positions. Here the camera calculates its position with just one image of the calibration target. Next step is to align the coordinate systems. This is done by an independent measurement system. In this case, we use a stereo camera system, which needs to be initially 3D measured. And then both coordinate systems are aligned together. And in the end, we need to apply these calibration data for our inspection of the windshields. So this is how the calibration procedure briefly is working. And of course, this is a system that we can easily also adapt in order to be able to inspect longer virtual image distances. talking about generating of the test pattern. We have mainly two different opportunities how we can compensate optical effects. The first one is using an aspheric mirror combined with a backlighted grid. Here, the rays are coming from the backlighted grid and are reflected on the aspheric mirror onto the windshield. With the use of the aspheric mirror, we can have a comparably straight image. The second option is the movable test grid with optical correction element. Here, for every single camera position, we can calculate a position for the test grid based on the simulation values that we receive. And to further improve the virtual image that we see, we can add an optical correction element to this whole system. And here you can see an example of an AR HUD virtual image using an aspheric mirror for all the different eyebox positions from the center position, left, right, top and bottom. Coming to the last point, the optical phenomena. So here, as I already mentioned, for longer virtual image distances, optical phenomena have an even greater and bigger influence, and therefore it is very important to have a good adjustment of the camera systems, especially regarding the depth of focus. Apart from that, we need a high camera resolution. And then the other point that we have is using an aspheric mirror and a movable test grid with optical correction element. As you can see, these challenges, they go hand in hand to a certain extent. And last but not least, we can correct remaining errors by using some offset values which we receive from the simulation, or where we can inspect an ideal windshield on the test bench. In the end, it remains for me to say thank you very much for your attention, and I'm really looking forward to see you in the Q&A session.